Hello, welcome back to PhysioDesigner Tutorial Series 4. In this tutorial series, we are going to create a model of human upright posture control on PhysioDesigner. In this time, we create the Model 3, which includes intermittent on-off switching control mechanism, by expanding the Model 2 which we created in the previous tutorial. Let's begin. We were considering the control mechanism of the human quiet standing posture by modeling the human body with an inverted pendulum. Important variables and parameters in the model are shown here. Theta is the tilt angle. Assume that the height to the center of mass is 1 meter, and weight is 60 kilograms. The gravity is 9.81 meter per second square, and T is the ankle torque. Do you remember that there are 5 types of the torques forming the ankle torque? 2 of them are related to the intrinsic mechanical impedance with passive stiffness and viscosity. Their other 2 are active neural feedbacks determined by delay tilt angle and angular velocity. The last one is noise torque. In the Model 3, we consider intermittent on-off switching of the neural feedback torques. Besides that, we use smaller stiffness and viscosity than those of the Model 2. And let's start with no noise condition. The intermittent on-off switching is defined depending on the state of the system, in other words, the position of the state point on the theta phase plane. When a state point is the highlighted regions in this slide, the neural feedback is off. The condition is described by this inequality. Under this condition, the fixed point corresponding to the upright posture is saddle type unstable. When the state point is in the highlighted regions, it flows towards the fixed point along the stable manifold, but after a while, it turns around and diverges along the unstable manifold. When a state point is in these highlighted regions, the neural feedback is on. In this time, the fixed point is unstable spiral. In this way, according to the position of the state point on the phase plane, the neural feedback torque switches its activation intermittently. Notice that, in either case, the fixed point is unstable in every moment. Let's check the dynamics by simulations. Okay, we will create the Model 3 by modifying the Model 2 including the noise torque that we created in the last tutorial. Load the Model 2. Instead of using Load menu, you can also drag and drop it on the main canvas. Click Open in the small dialog in this time, then open Physical Quantity dialog. What we need to do is to change the parameter P and D to variable parameter type, and define conditional implementation to switch its on-off. Find P, and change the type to variable parameter type, then go to Implementation tab. Select Conditional at the Definition Type combo box. In the first text box, a condition must be described. In this case, delay, theta, delta, times, delay, W, delta, minus A times delay, theta, delta, is greater than 0. In the second text box, a definition must be described. In this case, P equals 0.25 times mgh. We need to add the second condition. Click plus button. To define P for all other cases than the condition we now described, select else in the combo box, and define P equals 0. Similarly, we modify the definition of D. Change its type to variable parameter. Go to Implementation tab. Select Conditional in the combo box. Set the first condition. This is the same with the condition for P. Definition is D equals 10. Click plus button. Select else, and definition is D equals 0. For now, let's assume that the noise is absent. The parameter A is the slope of the on region on the phase plane. Now let's use minus 0.4. That's all. Close the dialog, and save the model as Model 3. Let's observe the dynamics of this model. Call Flint and run a simulation. plot theta, it's converging to the upright posture. Let's observe the orbit on the phase plane. You see, it makes interesting sawtoothed orbit converging to the fixed point. It started with the neural feedback on, so by unstable spiral orbit, the state point was pushed down. Then it entered to the off region, and the feedback was switched off. The state point moved along the saddle orbit, then entered the on region again. After that, this process was repeated. It's interesting to notice that the fixed point itself is unstable for every moment, but the state point is converging to the fixed point by the switching. Now let's add noise. Set 0.2 to the sigma, and run a simulation. Notice that theta is fluctuating not around the fixed point, unlike the case with continuous PD feedback in the Model 2. Sometimes it goes negative side, and come back to positive side. On the phase plane, you may still notice that there are parts of the orbit related to the spiral and saddle flow. Because of noise, the state point can go to opposite side of theta using a part of saddle flow. In summary, by switching two unstable vector fields properly, the fixed point can be asymptotically stable. Especially important to notice that the saddle stable manifold plays significant role to push the state point towards the fixed point. At last, let's try to modify the on-off condition a little bit. We will add a circular off region around the fixed point. Hence, the neural feedback is off when at least one of the first or second condition is fulfilled. Oppositely, the neural feedback is on when both of the first and second conditions are satisfied. Let's modify the model accordingly. Open Physical Quantity dialog, and select P. Go to Implementation tab. At the condition, add a second condition by separating double ampersand, which means and. Here, POW is a function taking two arguments, x and y, to calculate x raised to the power of y. We need to add the same condition to the definition of D. And the radius r is 0.004 in this example. Let's save the model as Model 4 and run a simulation. You see, this time the orbit converted to a periodic solution. Let's observe the dynamics with the noise. With the noise, the orbit did not stay in the vicinity of the fixed point, nor diverged. It interestingly fluctuated sometimes in the positive theta area, and sometime went to the negative side back and forth. This way of the fluctuation of the center of gravity is much similar with the human's fluctuation than that of the Model 2. That's all for this tutorial. Thank you for watching. Hope to see you next time. Bye bye.